Hello, scholars. Welcome to Chapter 3, Marine Provinces. Lots of information that we're going to learn all about the bottom of the ocean, its margins, its deep abyss, the mid-ocean ridge system, the biggest topographical feature on the entire planet. So much fun stuff for us to discuss today. Let's dive right in. Okay, in order to understand about marine provinces, we have to understand how we know that. So that's what bathymetry is, determining ocean depths and ocean floor topography so we can start to categorize and label. Echo sounding and satellites are efficient bathymetric tools that have helped us gain this knowledge of our ocean floors. Most ocean floor features are generated from plate tectonics, the driving force that creates mountains, landforms, generates new crust, so much good stuff that we talked about in last chapter. We'll look at different seafloor features that exist in different parts of the ocean. Cool. Bathymetry is basically elevation of the ocean floor. When we talk about elevation in terms of land, we talk about topography. Bathymetry is topography of the ocean floor. The very first bathymetric reading was by Posidonius in 85 BC, basically putting a big heavy weight on the end of a very long rope and dropping it down. He did this in the Mediterranean, starting to discover. One of the first people who, maybe not the first one who had the question, but who said, how deep is the bottom of the water underneath of me? Let's measure it. And he measured it, and old measurements were in terms of fathoms. Basically, it's the distance from one arm to one arm. Because you could measure 1, 2, 3. And so early measurements were in fathoms, the distance of arm's length for an individual doing the measuring, which was later standardized to a unit of measure to be 6 feet or 1.8 meters. Now, the HMS Challenger, a part of the British Royal Navy, was transferred to a science vessel and underwent a monumental expedition starting in 1872, measuring the ocean floor. And previous to this point, the ocean floor was believed to be flat. Previous to this point, the Earth was believed to be flat. So we're moving forward through systematic study, scientific observations, further increasing our understanding of how the Earth looks, how its form is, what its features are, how it functions, and the HMS Challenger was crucial in doing this. So they created, or another way to measure bathymetry, and we'll go through all of them here. Come on back. Perfect. Another way to measure bathymetry is through echo soundings. And you can use an echo sounder or a fathometer, and basically this is a reflection of sound signals that gives a ping. And it creates a two-dimensional map, but it lacks significant details and accuracy. It might even be slightly inaccurate, as the pings could reflect off of other layers that aren't the seafloor. But this started in 1925, and it's a step above line soundings or sounding lines. And so funny thing is the sounding line is a piece of rope with a heavy weight on it. There's actually no sound involved. But the further you get into echo sounding and then precision depth recording, which came about in the 50s, which is a little bit more accurate than echo sounding, really helped to confirm seafloor spreading by mapping mid-ocean ridges, these areas in the middle of the ocean that have an elevated profile and a deep rift valley right down through the middle of it. Moving further on, technology and time developed, and multi-beam echo sounders that allowed swaths of the seafloor to be recorded, and these seafloor strips up to about 37 miles wide started to give a more accurate representation of exactly what it is that's going on the ocean floor. So we're moving from a very coarse understanding. Echo sounding is just dropping a point in the water and saying, okay, there's a point here and a point here and a point here. It'd be like dropping a line from a hot air balloon as you're cruising across on a very overcast day, trying to say, how did the mountains look underneath me? I can't see them, but I'll take a point here and a point here and a point here and a point here. You wouldn't get a very accurate representation. But then echo sounding led to the PDR, led to multi-beam echo sounders, which leads to sonar, sound navigation, and ranging, basically sending out sound waves into the ocean and listening for the reflections of these sound waves. Now, a side scan sonar, work with me here, please. I apologize for the inconvenience. I really have no idea why it keeps clicking on and off like that. Fingers crossed that it just stays on for the rest of the time. So side scan sonar is basically towing an apparatus behind a boat that emits a beam out in two directions, and it gives you these full informational bathymetric profiles. Now it leaves a gap down the middle, but you can do transects to fill in these gaps, and you still get a pretty good idea of what is going on the ocean floor. Now that's things that we can do from boats, but we also have technology in space. So you can put a satellite in orbit and it can measure seafloor features based on sea surface elevations and the anomalies that come with the bulges due to gravitation. Pretty cool, using all the tools to understand. We can look at satellite-derived ocean surface gravity to reveal bathymetry where ships have not been before. So yes, you can tow an instrument behind a boat and you can take a transect and get a pretty good idea, but it's timely and the oceans are huge and we have not mapped the entire ocean floor. That's why it is almost the final frontier of exploration, because there's still so much we don't know about the oceans. We do know a lot. We've learned a lot, and it's awesome, but there's still a lot that we don't know. Satellites can give us global sea surface elevation. Really important for understanding how tides work, for understanding variability in Earth's magnetic field, for understanding, as we interpret the data, what the bathymetry of the ocean looks like in areas that have not been measured using other technologies. Another way that we can look and see what's going on in the ocean floor and even dive a little bit deeper than just the ocean floor surface is by seismic waves. So this is like an earthquake, a movement. But what happens when an earthquake occurs? Well, a seismic wave is sent out. This is how we know the composition of the Earth. The core, mantle, crust, varying layers, differences in density. Seismic waves have different wavelengths as they come down and reflect up. So a ship can set off an explosion and then with a receiver behind that record the different waves that are being reflected and create a subsurface diagram so we actually know what's happening not just on the ocean floor but underneath of it. Wow, that's amazing. Seismic waves tell us so much. And here we can see data that's been interpreted. So not only is the structure of the sea floor here, but we can pair it with a couple of seismic reflection profiles and see that there are layers of sediment, that there are contacts between these layers, and there are faults within these layers. Okay, what's happening at the bottom of the ocean? Let's take a peek. How do we do that? Creating a bathymetric profile using different types of technology, looking underneath the bottom of the surface of the ocean, utilizing seismic reflection profiles. So here this sums it up. How are we understanding the ocean floor? Okay, we've got a research vessel. It has an echo sounder, it has side scanning sonar, it's got a hydrophone, it's emitting explosions and recording their seismic profiles. It has GPS technology that's looking at the surface of the ocean. So many different ways. And this is how we know what the bottom of the ocean looks like, because we have recorded the elevations through all of these various techniques. From this information, we now know that the ocean has 3 major provinces. The mid-ocean ridge, which we've learned about in plate tectonics, deep ocean basins, and continental margins. And we see this really, really well in the Atlantic Ocean. Classic. Thanks, Atlantic, the Mid-Atlantic Ridge. Textbook. So great for studying. So we can see here on the east coast of North America, first there's a continental margin, and then a deep ocean basin that takes us to the Mid-Atlantic Ridge. On the other side of that is a deep ocean basin. And moving a little further is a continental margin again. Cool. There's 2 types of continental margins, active and passive, and it has to do with plate tectonics. If there are active plate tectonics that are going, the boundaries associated with convergent or transform plate boundaries, then we have an active continental margin. If it's not close to a plate boundary, now you are transitioning from continental to oceanic crust, but if there's no plate tectonic boundary, then it's passive. There's no tectonic activity. And we see active continental margins off the coast of the United States. We also see it off the coast of South America. This is the oceanic continental convergent plate boundary. There is subduction of oceanic lithosphere underneath continental crust, creating a narrow shelf, a deep offshore trench. We see these. We can observe these. And we notice this in bathymetric profiles around the world. The next type of active continental margin is going to be a transform continental margin, like the one running through California, San Francisco, LA. This green swath is the Central Valley. Hey, I can see my house from here. There's Fresno, and what we see is the North American plate is bounded by the Pacific plate, and there's a large fault. And so from here, continental to oceanic, bounded by a transform fault, we have an active continental margin. Now, who cares about active versus passive? Well, it's important for understanding how ecosystems work, the formation, the function, and the features, because each of them have different features associated. San Andreas Fault running through California. This is the Alpine Fault on the southern island in New Zealand. Here we see subduction above, subduction below, and connected by a large transform fault. The difference between land and ocean in this continental margin right here is going to be a transform continental margin, active continental margin. Continental margins have specific features. They have a shelf, a slope, and a rise. And you could say that the difference between the shelf and the slope is the shelf break. Let's talk about these. The flat zone from the shore to the shelf break is the continental shelf. It's part of the continent geologically. And there are average depths, but this is really going to depend on the type of continental margin, active versus passive, and the history. How old is this piece of land? Where is it located? If it's an active margin, what type of active tectonics? So there's averages, but I would like to say that how big are these? Well, it depends, and it's going to be very site-specific to the area of study. The continental shelf is a continental margin that determines shelf features. Well, here off of California, in this really interesting place. All right, cool. Got it. South of the San Andreas Fault, south of Santa Barbara, Los Angeles, we have the Channel Islands. And there's a series of features here because of the way that this continental margin is next to the San Andreas Fault that creates a transform active margin that's known as a continental borderland. Really cool geology going in here. Basically, the way that you have the transform fault moving, then you have a continental shelf at the same time. It's warping and twisting and folding the rocks into a series of peaks and troughs, anticlines and synclines, and parts of the anticlines that stick above are going to be known as islands, and we've got the Channel Islands here. Cool feature. California has amazing geology, so diverse. It's a great place to study and to learn about all of these ocean and geologic features. After the continental shelf, we have the continental slope. And it's a topography similar to land mountain ranges. It can range anywhere from 1 to 25 degrees, and it's marked by submarine canyons. Submarine canyons? What the heck is that? A narrow V-shaped notch cut into the continental shelf that can go all the way down to the continental rise. And they have very steep overhanging walls, and they can extend for long, long periods of time. This is the Monterey Bay. This is Monterey Canyon. Monterey Canyon is almost as big, if not bigger, than the Grand Canyon, and it's all underneath of water. Well, sea level was never low enough. We have not seen evidence that sea level was low enough that a river cut this. Underwater currents have carved out the Monterey Canyon, and these are called turbidity currents. Cool stuff. Turbidity currents are underwater avalanches mixed with rock and other debris. They move under the influence of gravity, and then they deposit sediments in these deep sea fans at their base. These sediments are called turbidite deposits, and they layer very similar to sedimentary rocks. Cool ocean features associated with continental margins. The last piece is going to be the continental rise. This is where the turbidite deposits are laid down, also known as submarine fans. And we get graded bedding, which we just saw in the previous slide. These deep sea fans or submarine fans can be very large. In fact, where the Indus River moves into the Indian Ocean, it brings a tremendous amount of sediment with it. That sediment goes underneath the surface of the water, carves out a large canyon, and then creates such a huge submarine fan that it goes all the way down here to the Carlsberg Ridge, through the continental slope, through the deep ocean basin, all the way to the mid-ocean ridge. That is significant. That's a lot of sediment. Perfect. Continental margins have a shelf, a slope, and rise. They carve out submarine canyons through turbidity currents, and they deposit turbidites and deep sea fans. Awesome. That's what we see here. Continental shelf. And then we move out to the abyssal plain. They extend from the base of the continental rise all the way to the mid-ocean ridge. These are the deepest, flattest parts of the entire planet. Way down there, way flat. They have accumulated settlement because all the debris that rivers transport and bring to the oceans moves through these turbidity currents, are laid down as turbidite deposits. Well, they're still super teeny tiny little particles that will travel further out into the ocean and then where it gets calm and deep, they will finally settle. Deep ocean basins, also known as the abyssal plain. These abyssal plains are marked by large underwater volcanoes, these volcanic islands. And they usually line up over a hot spot and travel at the rate of seafloor spreading. All of these are connected. Our whole Earth is connected, really. Oceanography, as we learned, is interdisciplinary. We're studying chemistry, geology, biology, astronomy, oceans. It's all connected, and it's so cool to think about the interactions, how all these things work. So if we zoom in, ocean basins from the three major provinces, the mid-ocean ridge, the abyssal plain, and the continental margin, they are all connected also. Here we can see different layers of the seafloor. How do we know this? Seismic reflections, very good. So using seismic reflections, we can gain a picture of the seafloor, and basically there's a subsurface topography underneath of it, created from the mid-ocean ridge, but then filled in with little sediments over time. Over millions of years, these start to fill in. Features that we would see, that we do see on abyssal plains, table mounts. When a volcanic island breaches the surface of the water, we call it an island. As it erodes, it will be eroded flat on top, and that's called a table mount. If that volcanic island never makes its way to the surface, we call it a seamount. And if it's just a little bit of a hill, less than a kilometer, we call it an abyssal hill. So, features classified by form and process. Ocean trenches create volcanic arcs. So at these convergent margins, we have deep ocean trenches. And here we can see the ring of fire. Why is it called that? Because there's so many volcanoes. In fact, there are more volcanoes and more earthquakes along this mountain range of volcanoes than anywhere else in the world. So much so that it needed its own name, and it was dubbed the Ring of Fire. We also have the deepest trench, the Mariana Trench, located in the Ring of Fire. And what this is an area that is so deep you could put Mount Everest inside of it, and there would still be 7,000 feet left over. Whoa, that's pretty deep. Two different types of arcs are associated with these type of margins: an island arc and a continental arc. Now, these are features that are created from subduction at these margins, this continental margin, where continental crust meets oceanic crust. The subduction happens, partial melting, density changes, we get these mountains on land. When it's happening with oceanic crust, we get an island arc. Examples of these would be the islands of Japan, island arc of volcanoes, the Andes Mountains in South America. Here again, we see the Ring of Fire zoomed in, marked by all these convergent boundaries. We've got a great documentary on the Pacific Ring of Fire that takes us into much more detail using rocks to understand the geologic history of an area. There's so many stories held within the rocks. It is the work of a geologist to investigate and interpret and understand that story by looking at what the rocks have to say. Our third major province is mid-ocean basins or mid-ocean ridges. This is the longest mountain chain because the mid-ocean ridge system extends like the seams of a baseball through the entire planet. It's awesome. It's big. It's volcanic, made of basaltic lava, and this is the primary type of divergent tectonic plate boundary. In the middle of the mid-ocean ridge is a rift valley, a downdrop area marked by fissures and faults with shallow, small earthquakes. So if I can wave my hands a little bit, we've got the edges of the ocean, continental margins. We've got the deep abyssal plain, longest, flattest places, deep ocean basins. And then we have, I'm going to turn my hands this way, we have the mid-ocean ridge that's elevated, and right in the middle is a rift valley. Now we see these rift valleys. What's associated with them are seamounts, volcanoes that are also in the area of the mid-ocean ridge. And the type of rock that they produce is basalt. And when the basalt erupts underneath the sea, it cools very, very fast into these pillow-like structures called pillow lavas. And you can see here, it's like one pillow on top of another, on top of another. Here's another image of recently formed pillow lavas. Very, very indicative, representative of mid-ocean ridge deposition. Some features associated with mid-ocean ridges: hydrothermal vents. They're like hot springs at the bottom of the ocean. There's very interesting deep ocean ecosystems, different creatures and critters and life that exists not from the energy of the sun, but through chemosynthesis, by surviving on the chemicals that is being moved through these different hydrothermal vents. A couple types of them, a few types. Warm water vents, it's like a hot spring. White smokers, temps from 30 to 350 degrees because the smoke they emit is white. Black smokers, temps above 350 degrees because the smoke they emit gives this dark color. Now, how do these work? Seawater infiltrates into the magma chamber, it heats up, and then it moves out in these different types of hydrothermal vents, depositing different features and then emitting all kinds of nutrients back into the water. So in essence, these hydrothermal vents are like the kidneys of the ocean. All ocean water filters through these hydrothermal vents on the order of every 7 million years, and it keeps the chemistry of the oceans relatively stable. How cool is that? It's like a body part of the ocean that makes sure that its chemistry is held stable. I love that. Associated with mid-ocean ridges are transform faults and fracture zones. So mid-ocean ridges aren't perfectly straight. They have offsets for connecting different parts of the divergent boundary. And these offsets, here's the divergent boundary, seafloor spreading. Here's the divergent boundary, seafloor spreading. The space between these is a transform fault. Now, on the opposite side is a fracture zone where it will still undergo movement and shifting, faulting, but you will not have this dedicated side-to-side horizontal movement as you do in the space between these two. Divergent plate boundaries go hand in hand with these transform faults and fracture zones. Perfect. We have volcanic activity associated with mid-ocean ridges, and it creates new ocean islands. And here we can see some smoke being emitted because a lava is flowing from one of its vents. It's coming down here, touching into the water. Smoke is rising. How awesome is this? Islands are being created right before our very eyes. The big island of Hawaii, the active volcano of Mount Kilauea, erupts often, and it creates new crust, and it is these ocean processes in action. So to summarize our marine provinces, there are 3 major marine provinces: There are continental margins, deep ocean basins, and mid-ocean ridges. Margins have a shelf, a slope, and a rise that connects to a deep ocean basin that has an abyssal plain full of different volcanic features filled in with lots of sediment that connects to a mid-ocean ridge that's elevated, has a rift valley, transform faults, erupts new oceanic lithosphere, and when it does, it comes in the form of pillow basalts. All three of these provinces work together to create the bottom of the ocean. And we know a lot about this because we have mapped the elevation of the ocean floor using the various bathymetric methodologies to create really comprehensive maps that show us so we can see the form and learn the function of our ocean basins. That's our chapter for today. I know I speak really fast. I get very excited. I also post the lecture slides with every single lecture. That way, if you need to go back and look at something again, it's available for you. I hope my pace isn't too fast. I apologize if it is, but I'm just really happy and excited to share all this awesome information about the oceans with you, and that's where it comes from. So thank you for listening. I appreciate your attention, and we'll see you in the next one.